Our next presenter is Kevin Burdge, who did a project on holographically computing the entanglement entropy of an annulus in a strongly coupled conformal quantum field theory.
Okay, full screen. Can we make it? Okay, so this mouthful of a title is actually just a computation in theoretical physics relating to the behavior of particles. So when we classically think of particles, like in the context of projectile motion, a particle has like a definite position and a velocity, and we predict its behavior based off of that. In our calculation, the particles we're working with are governed by the laws of quantum mechanics. The important thing here is instead of having a definite position, a particle is sort of spread out over different positions, and it has a specific probability of being in each position if you observe it. The key is that before you observe it, it occupies multiple positions at once. Its probability distribution here is defined by something called the wave function, which to actually get this graph, you take the square of the modulus of the wave function. The important thing is when you observe it, this wave function does something called collapsing, and when the wave function collapses, the particle descends to a specific state. Like you guys all know the whole Schrödinger's cat thing being both dead and alive, but when you observe it, then the cat's wave function collapses. Okay, so these particles, they interact with each other very dynamically. We describe these interactions with something called quantum field theory. In quantum field theory, you describe the interaction of particles with something called a Feynman diagram. This Feynman diagram illustrates what you guys are probably familiar with as the electromagnetic force, like charges repelling each other. In the diagram, you see two electrons repelling each other, and what actually causes that in the quantum field theory is the electrons sort of spit photons at each other, and that results in this repulsion. So these diagrams have many, many perturbations where you can have some interesting, add-on interesting things that happen. Like here, the photon turns into a positron and electron pair that then quickly decide, oh, we can't exist, and then they annihilate each other and become a photon again. So with weak forces like the electromagnetic force, all these variations, the more complex you make them and the more squiggles you add, and believe me, you can add a lot of squiggles, the less it actually matters. However, in other field theories that work with strong forces, like the strong force that binds the nucleus of an atom, every variation does matter, which makes these immensely complex. So our field theory that we perform this calculation in is a strongly coupled theory, which just means we're working with the force of this nature where the perturbations do matter. Okay, so the phenomena we're dealing with that we're calculating has to do with entanglement. So earlier I mentioned that particles can exist in multiple states, and when you observe it, the wave function collapses and they go into one specific state. So say you picture these particles as people. Now you have a box, and it's got a right glove and a left glove in it. And two different people go up to the box, and each one takes a glove, and then they conceal which glove they took. So each one took one glove, and you observe none of this. And they've got their hands in their pockets now. To you, technically now, both these people are both right-gloved and left-gloved because their wave function hasn't collapsed. So now say these two people walk miles apart and you follow one. If the other guy that you're not observing now reveals this glove, his wave function collapses. He becomes either right-gloved or left-gloved. But the important thing is your guy's wave function also collapses as a result. And that's called entanglement. The states of the two particles are related to each other. They're entangled. So what we're calculating is actually an entanglement entropy. So first of all, what's an entropy? An entropy describes the unpredictability of a system. You guys probably associate it with, in chemistry, solids have lower entropy than gases. Well, if you think about it, a solid, all the atoms are in a lattice, they're not really moving around. It's a pretty predictable system. Nothing wild's going on. Whereas in a gas, it's very dynamic. Things are moving very quickly. It's a very unpredictable system. So our entropy is an entanglement entropy, and this is in a quantum field theory. So let's extend the metaphor we used earlier of the people with the gloves, and now let's say 100 of those people are MIT students. And they all inhabit this region in a quantum field theory, this circle, and we know everything that goes on there. We have 24/7 surveillance. We know all the interactions. So these 100 students go out, say, to the park, and they meet up with 100 strangers, and each one of them reaches into a box with the stranger, and they entangle themselves, their glove state with the stranger, and they all go back to the MIT campus and it's concealed. So you know everything that's going on in this region, but now there are 100 strangers somewhere out here in Boston or around the world that are entangled with 100 of the particles in your region. And if any of these people reveal their gloves and cause their wave functions to collapse, it causes your MIT students' wave functions to collapse as well. That's adding to the entropy of your system. That's something you can't predict because you know absolutely nothing about those strangers outside of your region. And that's the quantity we're calculating. So how do we calculate this? We use a principle called holography that comes from string theory. So holography basically states that there's an equivalence between a quantum field theory in d dimensions and a curved spacetime in d+1 dimensions. Okay, what does that mean? So say you have a two-spatial dimension region in a quantum field theory. There's also a time dimension, but just for the sake of simplification, two spatial dimensions. And you use the holographic principle to translate it to a curved spacetime. What this adds is it adds a third dimension, which basically forms a solid bowl under that circle. The interesting thing that holography states is that if we find the minimal possible surface area of this bowl surface, it gives us the quantum or the entanglement entropy of the region in the quantum field theory. It's a fascinating principle. So we performed a computation using holography to calculate a quantum entanglement entropy, but the interesting shape we used is we used an annulus rather than a circle. Why an annulus? So earlier I stated that the shape sort of hangs down and forms a bowl under a circle. Well, with an annulus, if you look at the cross-section, there are really two ways it could hang down. You can either sort of have a bowl within a bowl, or you can have what looks like when you cut a bagel, so the flat surface of the bagel, and then you've got the part hanging down. A key difference here is that in one, the region inside is connected to the outside. The other one, that's not the case. And our hypothesis was that if you vary these values, rho 1 and rho 2, which are the inner and outer radii, there would be a phase change. You'd have a change where the donut would have less surface area, but then the bowl would have less surface area. And the prediction was if you move rho 1 and rho 2 really close to each other, the giant bowl it forms would have more surface area than the little donut. So we did a calculation to find the possible solutions for this, and it turns out there are two different donut solutions. One is like the one we predicted, and there's another one that actually forms this shape. It's almost more like a bowl shape with a hole in it. And then the known solution was the bowl within a bowl. So which one do you guys think has the least surface area? Turns out that the one with the least surface area is the giant bowl. Now, why is that? Well, we're doing a calculation in a form of curved spacetime called anti-de Sitter space. And because it's curved spacetime, when you calculate the surface area, this is the integral, don't panic. You guys probably recognize the whole surface area. This is the length of a line, an arc or something, and then you rotate it around 2 pi and you integrate it and you get surface area classically in calculus. Well, because we're in curved spacetime, we add in this term, 1 over z of rho squared. So when z is very small, the vertical axis is the z-axis, it causes the surface area of our shape to skyrocket asymptotically. So the more time the line spends away from z equals 0, the less surface area. And you also have this rho term in there that causes this donut to try to flee towards rho equals 0. That's why it wants to minimize that as well. So so there was never a phase change. No matter what you do to rho 1 or rho 2, there's never a phase change, which means that inner region is always isolated. So this is purely speculation, but some interesting consequences should be investigated. Why does that inner region always have to be isolated? Does that have some meaning about the entanglement of the inner region and how it relates to the outer region?